Good afternoon, ladies and gentlemen. My name is Kiwilsza. I am a PhD student at the Faculty of Physics at Kiwilsza in Poland, and also at the Nanotechnology Center. It's my great pleasure to be here for the second time and present to you some of my results. The title of my presentation is Order for Certain Materials for Selected Anti-Hypertensive Drugs. But due to the limited time, I will focus on only one type of drug, which is the nimodipine, and only one type of mesoporous silica, which is SBA. The outlines of my talk is the following. First of all, I will say a few words about the aim of my study, then I will present the drug and silica matrix. I will say a few words about the drug loading procedure. I will show some results of crystallinity verification and molecular dynamics study. I will present the drug dissolution study, and then I will summary my talk. According to a series of epidemiological studies on hypertension in Poland, about 30% of adults suffer from abnormally high blood pressure. It is reported that another 30% of adults will face this problem in 5 years' time because of bad lifestyle. It is also reported that in 2025 about 14 million Polish people will suffer from hypertension, but unfortunately, using available products on the market, only 25% of them are properly treated. Here you can see the graph presenting most of used products in hypertension treatment. Here it is the calcium channel blockers, which are I'm focusing on in my study. So the aim of my study is to prepare a system which could be implemented in the future. Nimodipine is the second generation calcium channel blocker. It is used for treatment of blood circulatory disorders, especially in the brain. It's not hygroscopic and not sensitive to temperature, but it's easily photodegradable. And it's practically insoluble in water. And in order to increase its solubility and prevent the photodegradation, some of order mesoporous silica should be implemented to improve to disadvantages. Nowadays, it is administered orally, but we have to use very high doses of this drug, or it could be implemented intravenously, but this kind of application causes pain and inflammation. In our study, we used as order mesoporous silica SBA15. It was synthesized using method presented by Zhao and co-workers. It is a typical hydrothermal condensation reaction of Theos hydrolysis products on a polymer template, as you can see in this TM picture. Sorry. They are shaped as rod-like particles, and they are very, very long, and they have about 500 nanometers in diameter. The pores, the mean pore size in this material is about 6 nanometers. So nimodipine can be loaded inside the pores. Here it is the drug loading procedure is presented, but I'm not going to describe it in details. What is important in this slide, it is that we studied our sample without washing procedure and also after washing it with the chloramate. First of all, we would like to check whether our drug is really loaded inside the mesoporous silica matrix. So we performed the nanogrammatometric analysis. Here you can see the results of it. For unwashed sample, we have about 50% of drug loading. After washing, it is reduced to 20%. In order to check whether our drug is in crystalline or in amorphous form, we performed three different studies using three different techniques. First of all, it was the differential scanning calorimetry. As you can see in this slide, here for pure drug we have the peak of crystalline melting of nimodipine. Here in unwashed sample it is also present. In washed sample there is no melting of crystalline form. And the same results is shown here. We don't have any crystalline peaks in washed sample. Another confirmation of amorphicity of our drug after loading and washing is the infrared spectroscopy. Here, the main changes may be observed in two regions. Here, about 2,300 and about 1,070 centimeters reversed. Here, in unwashed sample, we can see a band coming from crystalline form and also some band coming from the amorphous form. After washing, we only have the band coming from the amorphous form. Another method that really confirmed our amorphicity of the drug is NMR technique. After examining the unwashed and washed sample, we can see that the peaks coming from crystalline nimodipine disappear, and we have only the amorphous form of our drug. We also wanted to study the molecular dynamics of our drug. First of all, we did the measurements for the pure drug, then for the unwashed sample, and here we can see that we have two components, one coming from the crystalline form of the drug, and the second one from the amorphous one. But this component is different from that we have in washed samples. So it can be concluded from this experiment that the amorphous state of our drug after washing is quite different from this in unwashed samples. And finally, the results which join our study with the application of such system is the dissolution study of our samples in water environment. Here you can see the drug release, the nimodipine release, which is limited by the water dissolution of this drug. Physical mixture and unwashed sample is similar with the pure drug, so it is also limited. When we apply the drug loading and washing, almost full amount of the drug is released, and it is done in the first hour. So this kind of nanocarrier improves the dissolution of the nimodipine. And to summarize my talk, I would say that hexagonal arrangements for silica material can be applied as nanocarrier for poorly soluble drug. In this case, it was nimodipine, and using modified adsorption from the solution method, we can obtain a stable system with 50% of drug loading before washing and 20% of the drug loading after washing. According to the results of several methods, during encapsulation, it was possible to obtain nimodipine in amorphous state, and this state was characterized by different molecular dynamics than for crystalline drug. And some dissolution experiments showed a fast and complete release of nimodipine included within the SBA 15. These are the co-authors who helped me doing these experiments, and I would like to thank you for your attention.
So thank you for the report. So are there any questions? Okay, please.
You told that your drug is fully dissolved in water, yes?
No, it's not dissolved in water.
Yes, but after mixing with SBA, it's dissolved in water? Or what?
Yeah.
And can you explain why this process occurs?
Because when we have the crystalline form of the drug, each molecule is very close to each other. After amorphization, the molecules are more separated. The surface area of the releasing process is higher.
Okay, and I have a question about using this composite for basically anti-hypertensive for treatment, medical treatment. Is it ready for using or not yet, or what is needed to use it?
This is the preliminary study. Because of the size of this material, it should be implemented orally only, because the SBA rods are too long to be, for example, included in the bloodstream. But I think in the future, after doing some other experiments, especially the release one with not water but with simulated body fluids, it can be implemented.
Okay, thank you. So, one more question.
A typical problem that occurs with this system is that it's difficult usually to establish if the drug actually entered into the channel of the mesoporous. So, in your case, which are the experimental evidence that the molecules entered in the channel and not just deposited on the external surface?
Actually, we hope that before washing, we have something inside the pores and the rest, which is crystalline, on the surface of this material. After washing, it's not really proof, but we hope that it's inside the pores. Because if we had it on the external surface, I think that the release profile should be similar that for the pure drug. But
why not you try with the non-porous silica?
Actually, we have this material, so we tried with them.
Yes, but anyway, non-porous silica widely available commercially, they're very cheap.
Yeah, that's the reason.
Okay, thank you very much.